right-hand rule describes the direction of the magnetic force to a charge due to a magnetic field. When a charged particle is moving through a magnetic field, a magnetic force acts on it. This force has a maximum value when the charge moves perpendicularly to the magnetic field. The direction of the magnetic force depends on the direction of the magnetic field and the direction of the velocity of the charge. In addition, a positively charged particle will be deflected by a force in a direction opposite to that of a negatively charged particle. The magnitude of the magnetic force can be calculated using the formula F is equal to Q times V times B times the sine theta. F is the magnetic force measured in newtons. Q is the absolute value of the charge of the particle measured in coulombs. V, the velocity of the charge measured in meters per second. B is the magnetic field measured in Tesla. And the angle here is between the magnetic field and the velocity of the charge. The direction of the magnetic force can be identified using the right-hand rule. As an example, we look at a proton moving 8,000 meters per second along the positive x-axis. It enters a region in which there is a uniform magnetic field of magnitude 2.50 Tesla directed in positive y-axis. Find the magnitude and direction of the magnetic force on the proton. To have a better understanding of the problem, we draw a diagram showing the given quantities. We indicate the direction of the magnetic field, which is along the positive y-axis, and the velocity of the charge is to the positive x-axis. The velocity is 8,000 meters per second. The magnetic field is 2.5 Tesla. Proton is 1.6 times 10 raised to negative 19 coulombs. The angle between the velocity and the magnetic field is 90 degrees. We are looking for the magnetic force. We will get a magnetic force of 3.2 times 10 raised to negative 15 newtons by using our formula. Remember that the unit Tesla is the same as Newton per meter ampere, and ampere is the same as coulomb per second. Therefore, if you eliminate all the units, you will end up with Newton. The direction will be identified using the right-hand rule. But how do we use the right-hand rule again? Let's have a review first. The following are the common symbols used to indicate directions. For north or along the positive y-axis or up, we use an arrow pointing upward. A left arrow for west or along the negative x-axis. An arrow pointing downward for south or along the negative y-axis. For right and east or along the positive x-axis, we have an arrow pointing to the right. For 3 dimensions, we have an X mark inside the circle to indicate a direction pointing into the board, into the paper, or in our case, into the screen. For out of the screen or out of the board or paper, we will use a point inside a circle. The point inside the circle symbolizes the head of an arrow, while the X mark symbolizes the tail of the arrow. The magnetic field and the velocity lie on the same plane. In this example, the plane is in the X and Y plane. Alternately, you can imagine these two directions appear as a single line when viewed at a certain angle. The magnetic force is always perpendicular to this plane or to the line. You can say that the magnetic force is along the z-axis. You can emulate this using your right hand. Your 4 fingers correspond to the magnetic field, while your thumb is the direction of the velocity. The direction where your palm is facing is the direction of the magnetic force. This is in the case of a positively charged particle. Remember to take the opposite direction when you are dealing with a negatively charged particle. Let's do some practice. Let's say we have a magnetic field to the right and a positively charged particle moving upward. Position your 4 fingers to the right and your thumb upward. You will notice that your palm is facing into the screen or into the board. That is the direction of your magnetic force. For the second one, we have magnetic field upwards and a positively charged particle moving to the left. The magnetic force will be into the screen as well. Next, we have magnetic field upward, and this time a negatively charged particle moving outward or out of the screen. Your palm will face to the left but will take the opposite of it, which is the right side as our direction because we are dealing with a negatively charged particle. How about if we have a positively charged particle moving out of the screen along a magnetic field which points downward? The magnetic force would be to the right. Next is a magnetic field into the screen and a negatively charged particle moving down. The direction of your magnetic force should be to the left. How about the third one? Your magnetic field is into the screen again, but we have a positively charged particle moving to the right. The magnetic force should point upward. Try to do this one. You have a magnetic field to the left and a negatively charged particle moving into the screen. The magnetic force should point downward. The second one, magnetic field out of the screen and a positively charged particle downward. The magnetic force should be to the left. For the third one, magnetic field is out of the screen, a negatively charged particle moving upward. The direction of your magnetic force should be to the left. Now, what if the angle between the magnetic field and the velocity is not 90 degrees? For an angle between 1 degree until 179 degrees, we will treat them as if they are 90 degrees. Therefore, they will have the same direction, but since they have different sine theta, they will have different magnitude. As for 0 degree and 180 degrees, there will be zero magnetic force. So for the first example, even though they are not perpendicular, we can still point our four fingers upward and our thumb to the right. Your palm will be facing out of the screen, but since we are dealing with a negatively charged particle, we'll take the opposite direction. So the direction of the magnetic force is into the screen. For the second one, our magnetic field is upward and our velocity will be to the left. Since we have a positively charged particle, the direction of your magnetic force should be into the screen as well. Now, if we go back to our original problem, the magnetic field is pointing upward and we have a positively charged particle moving to the right. The direction would be out of the screen. And that's how to use your right hand rule. And that's it for me today. As usual, correct practice will make you better. So keep solving.